Hello, find a comfortable place. Let the sounds of your room fade away and let your breathing slow down. Tonight, we're not going to look at the world around us, but at the home above us. Let's begin our journey by imagining we are stepping outside on a perfectly clear dark night. We are far away from the glow of city lights in a place where the sky is so black it feels like you could fall right into it. When you look up past the familiar twinkle of the brightest stars and the steady light of a wandering planet, you'll see it. A soft, hazy band of light stretching from one end of the horizon to the other. It looks almost like a cosmic cloud or a river of spilled light. The ancient Greeks called it Galaxias Kyklos, the Milky Circle. We simply call it the Milky Way. It looks so peaceful, so static, so incredibly far away. But that beautiful misty light, it's a profound illusion. It's not a river, and it's not a cloud, it is a city. A sprawling, luminous city made of stars. Not thousands, not millions, but hundreds of billions of them. And we are not just looking at it, we are in it. We are residents of this city. The reason it looks like a faint band is because we are seeing it from the inside looking out. Imagine standing in a quiet neighborhood of a vast flat city at night. If you look toward the dense bright downtown, you wouldn't see individual streetlights, but a combined hazy glow. When we look at the Milky Way, we are doing the same thing. We are standing in our own quiet street, looking edgewise into the dense, bright, populated disk of our home galaxy. We are seeing the combined, unfathomable glow of billions of distant fellow suns. If we could somehow take a ship and travel thousands and thousands of light years, straight up above the city, and then stop and look down, what would we see? We would see its true shape, a magnificent swirling vortex of light. Our galaxy is what astronomers call a barred spiral. At its very heart, there isn't just a point of light, but a dense, glowing bar of stars, perhaps 27,000 light-years long. And from the ends of this bright central bar, great spiral arms made of gas, cosmic dust, and billions of newborn stars, sweep outwards like a cosmic pinwheel. It's a structure of unimaginable grace and scale, spinning slowly in the darkness. But where are we in this grand design? Are we in that bright, chaotic central bar? Are we in one of those grand, sweeping main arms? No. Our star the Sun and our tiny, fragile blue world, we are located in a much quieter, smaller section. It's a kind of partial arm or spur known as the Orion spur. We are nestled gently between two of the major grander arms, the Perseus arm and the Sagittarius arm. We are in galactic terms in the suburbs, and this location, this quiet, relatively peaceful spot, might be one of the most important facts for our existence. We're not too close to the violent radiation of the chaotic center. We're not too tossed around by the gravitational pushes and pulls of the denser main arms. This stellar tranquility may have been the very thing that allowed us, the billions of years of relative stability needed to emerge to think and to finally look up and wonder where we are. Let's take a journey in our minds. Let's imagine we can fly out of our quiet spur and drift toward that bright central hub. The closer we get, the more crowded it becomes. The stars here are not the lonely points of light we know. They become a dense, glittering fog, a swarm of ancient golden suns, packed incredibly close together. The energy is immense, a beautiful and chaotic storm of light and gravity. And then, as we push through this stellar haze, we arrive at the very center, the precise gravitational heart of our entire galaxy. We might expect to find a giant, brilliant star, a king sun, but we find the opposite. We find darkness. It's called Sagittarius A star. It is a supermassive black hole, a presence with the gravitational pull of over 4 million suns all compressed into a single dark invisible point. We often think of black holes as monsters, as cosmic vacuum cleaners that roam the universe devouring everything. But this one, it's more like a quiet, unseen anchor. It is the dark, heavy heart around which our entire luminous city pirouettes. It doesn't hunt. It simply is, and its immense presence provides the central anchor, the gravitational pivot point that orchestrates the elegant slow dance of our entire galaxy, including our own sun, 26,000 light-years away. Everything we see and everything we are is in a gentle cosmic freefall around this single dark point. But our city isn't just the flat disk, the downtown and the suburbs that we live in. Surrounding this entire spinning wheel of light is a vast invisible sphere, a halo of dark matter, thin gas, and ancient scattered stars. And floating within this enormous halo, like embers from an ancient long-dead fire, are the globular clusters. These are magical to behold. They are not like the loose gatherings of young blue stars in the spiral arms. A globular cluster is a tight, gravitationally bound perfect sphere of hundreds of thousands, sometimes millions, of stars. They are the galaxy's senior citizens. These are the ancient families the firstborn stars formed when the Milky Way itself was just beginning to take shape 12 or 13 billion years ago. They are like stellar time capsules orbiting far above and below the main disk, holding the chemical secrets of our galaxy's infancy. So the next time you're outside under that quiet dark sky, look up at that faint shimmering band. You're not just seeing a distant object. You're seeing home. You're seeing the grand architecture of your own cosmic neighborhood. You're seeing the collective light of billions of sibling stars all moving together in this grand slow dance anchored by a dark heart. The Milky Way is not just something we see, it is where we are. The very atoms in your body, the iron in your blood, the calcium in your bones, the oxygen you are breathing right now, were forged in the fiery hearts of stars that lived and died within this very galaxy long, long before our sun was ever born. You are in the most literal sense a child of the Milky Way. You belong to this structure just as it belongs to you. You are home. As we find ourselves resting on this quiet pale blue dot orbiting an average star somewhere in the vast spiral arm of our Milky Way, it's easy to feel like our galaxy is the entire universe. It truly feels like an island out of light floating in an endless dark ocean. But it's not alone. If we could quiet our minds, step away from all the noise and the light of our world, and let our eyes adjust to the deep cosmic dark, what would we see? What lies just beyond our own shores? What neighbours do we have in this magnificent emptiness? There is one in particular that calls to us. On a perfectly clear, moonless night, far from the lights of the city, you can just barely see it with your own eyes. It's not a sharp point of light like a star. It's a smudge, a faint, blurry, elongated patch of light in the constellation Andromeda. For centuries, astronomers didn't know what it was. They called it the Andromeda Nebula, thinking it was a cloud of glowing gas inside our own galaxy, perhaps a place where new stars were being born. But in the 1920s, we learned the profound truth. That faint smudge is not a cloud, it is another galaxy. A completely separate island universe, just like our own, but seen from an immense distance. We call it the Andromeda Galaxy, or M31. It is our great neighbour. In many ways, it is a mirror of ourselves. It's a massive spiral galaxy, just like the Milky Way, with sweeping arms of stars and dark lanes of dust. But it is the big brother in our cosmic neighbourhood. While we estimate our Milky Way has perhaps 200 to 400 billion stars, Andromeda is home to 1 trillion. It's larger, more massive, and shines brighter. When we look at it, we are seeing the light that left it 2.5 million years ago. We are quite literally looking 2.5 million years into the past at a place that looks hauntingly like home. But Andromeda is more than just a beautiful distant neighbour. It's our future. You see, in this expanding universe, most galaxies are moving away from us. As the fabric of space itself stretches, it carries them further and further away, their light stretching into the red end of the spectrum. Andromeda is one of the few exceptions. It is moving toward us. It's racing toward the Milky Way at an incredible speed, about 250,000 miles per hour. It is caught inextricably in our mutual gravitational pull. This means we have an appointment. In about 4.5 billion years, our two great galaxies will meet. Now when we hear the word collision, our minds imagine a catastrophic crash. Cars smashing glass, shattering stars exploding. But that's not what will happen. Space is mostly space. The distances between individual stars are so immense that when these two galaxies merge, it's exceptionally unlikely that any two stars will actually hit each other. Our own sun and solar system will almost certainly be fine, though perhaps tossed into a new strange orbit. Instead of a crash, it will be a dance. It will be a slow, majestic gravitational ballet that will last for billions of years. The two spiral galaxies will first fly past each other, their gravity pulling and distorting their beautiful familiar shapes. Long tails of stars and gas called tidal tails will be flung out hundreds of thousands of light years into the void. They will pass through each other like two magnificent ghosts, and then gravity relentless and patient will pull them back, and they will pass through each other again. Over hundreds of millions and then billions of years, they will slow down, their structures will be completely disrupted, and they will settle. They will merge. The two spirals will combine to form a single enormous new galaxy. This new galaxy won't be a spiral, it will be a giant elliptical galaxy, a massive roundish city of stars glowing with the light of its new combined population. Scientists have already given this future home a name, Milkomeda, or perhaps Milkdromeda. It's a strange and profound thought that the night sky our distant descendants might see, if any are around, will be completely different. It would be dominated not by the pale, familiar river of our own galaxy, but by the chaotic, brilliant and beautiful birth of a new larger one. It is a destiny written in the laws of gravity. Andromeda and the Milky Way are the two heavyweights, but we are not the only members of this family. We are all part of a structure we call the local group. Think of it as our cosmic county. It's a small cluster, a neighbourhood of about 50 to 80 galaxies all gravitationally bound to each other, all moving through the universe together. Most of them are small, dwarf galaxies. These are faint, sometimes disorganized collections of just a few billion stars or less. The third largest member after Andromeda and us is the Triangulum Galaxy, or M33. It's a beautiful smaller spiral, and it might actually be a satellite of the larger Andromeda Galaxy caught in its pull, destined to one day merge with it as well. And then there are our closest companions. If you are fortunate enough to be in the southern hemisphere and look up at the dark sky, you can see them clearly. They look like two detached hazy clouds separate from the main band of the Milky Way. These are the Large and Small Magellanic Clouds. They are not clouds of gas or dust. They are small, irregular dwarf galaxies. They are our satellites. They are the moons of the Milky Way orbiting us just as our own moon orbits the Earth, though on a much, much grander scale. They are so close that our Milky Way's immense gravity is tearing them apart, pulling streams of hydrogen gas from them in what we call the Magellanic Stream. They are being slowly, gently consumed by our own galaxy. So what does it mean to be part of this local group? It means that even in the unimaginable vastness of the cosmos, we are not isolated. Our island is part of an archipelago. We belong to a family held together by the same fundamental force that keeps our feet on the ground and our planet circling the sun. We are in a constant slow dance with these neighbours. We are shaped by them and they are shaped by us. When you look up at that faint fuzzy patch of Andromeda, you're not just looking at another galaxy, you're looking at a relative. You're looking at your future, and you are seeing a profound truth that everything that is connected. For centuries, astronomers looked at the night sky and saw a beautiful starry river of light, our Milky Way. They also saw faint fuzzy patches like tiny glowing clouds. They called these nebulae, the Latin word for clouds. Some looked like pinwheels, others like fuzzy balls. The biggest question in astronomy, known as the Great Debate, was simple. Were these nebulae small gas clouds inside our own Milky Way, or were they something far, far more profound? The answer came in the 1920s from an astronomer named Edwin Hubble. Using the powerful new 100-inch Hooker telescope on Mount Wilson in California, he stared at one of the most famous nebulae, a fuzzy patch in the constellation Andromeda. He wasn't just looking at it, he was hunting for something specific inside it. He found it a special kind of star called a Cepheid variable. This was the key. Cepheid variables are cosmic lighthouses. They don't just shine, they pulse, getting brighter and dimmer in a precise, regular rhythm. Decades earlier, an astronomer named Henrietta Leavitt had discovered a remarkable secret. The speed of this pulse is directly connected to the star's true brightness. Imagine you see two light bulbs. One looks bright, one looks dim. You don't know if the dim one is actually a dim bulb up close, or if it's a very powerful bulb that's just extremely far away. But what if you knew that all 100-watt bulbs flash exactly once per second, and all 25-watt bulbs flash once every 5 seconds? By timing the flash, you would know its true wattage. You could then compare its true brightness to how dim it appears, and calculate its exact distance. This is exactly what Hubble did. He measured the pulse of the Cepheid star in the Andromeda Nebula. He calculated its true brightness. He compared it to its apparent dimness. His calculation was staggering. The distance to Andromeda wasn't thousands of light years away, which would place it inside our galaxy. It was, by his initial calculations, nearly 1 million light years away. We now know it's closer to 2.5 million. The Milky Way itself is only about 100,000 light years across. This was the moment the universe shattered its container. Andromeda was not a cloud. It was an island universe, an entire galaxy just like our own, teeming with hundreds of billions of its own stars, its own planets, and possibly its own life. And if Andromeda was a galaxy, then all the other pinwheels and fuzzy blobs in the sky were also galaxies. In an instant, the known universe expanded from one galaxy, our own, to a countless, endless ocean of them scattered through the dark in every direction. We were no longer the center of everything. We were just one island in a cosmic archipelago of billions. The cosmic zoo. Classifying galaxies, once Hubble proved these islands of light existed, he realized they weren't all the same. Just as a biologist finds new animals and needs to sort them into species mammals, reptiles, insects, Hubble needed a way to sort the galaxies. He created a classification system that is still used today, famously known as the Hubble tuning fork diagram. He organized the galaxies based on what he could see their shape or morphology. He found they fell into a few main categories, creating a cosmic zoo of different galactic species. Spiral galaxies. These are the beautiful grand design galaxies, the poster children of the cosmos. Our own Milky Way is a spiral galaxy. Our nearest large neighbour Andromeda is also a spiral. They are defined by three main parts: the bulge, a bright dense spherical ball of stars at the very centre. This region is mostly made of older yellowish red stars. The disk, a thin flat rotating plate of stars, gas and dust that surrounds the bulge. The arms, majestic curving arms that spiral out from the centre located within the disk. Spirals are the growing cities of the universe. Their disks are full of vast cold clouds of hydrogen gas and cosmic dust. This is the raw material, the lumber and bricks needed to build new stars. The spiral arms themselves are not solid objects. You can think of them as cosmic traffic jams or density waves. As the disk of the galaxy rotates, these waves move through it. Much like a wave moves across an ocean, the water itself doesn't travel, but the wave does. When a cloud of gas hits this traffic jam, it gets squeezed and compressed. This compression is the trigger. Gravity takes over the cloud, collapses in on itself, and a new generation of stars is born. This is why the spiral arms are so bright and easy to see. They are filled with brand new massive stars. These stars are incredibly hot, and because they are so hot, they shine with a brilliant blue-white light. They also burn through their fuel extremely fast, living for only a few million years before exploding. The arms are therefore the construction sites or stellar nurseries of the galaxy, glittering with newborn blue stars. Elliptical galaxies. If spirals are the busy growing cities, elliptical galaxies are the ancient retired cities. They are the simplest looking galaxies in the zoo. They are just massive three-dimensional fuzzballs of light. They can be shaped like a perfect sphere or a long stretched out football and ellipsoid. They have no disk, no spiral arms, and almost no construction material that is. They have very little cold gas and dust. Because they ran out of gas billions of years ago, they cannot make new stars. The stars inside them are almost all ancient. They are population 2 stars which formed long ago and have been shining ever since. These stars are old, cool, and glow with a soft reddish yellow light. An elliptical galaxy is a vast, quiet, retired collection of hundreds of billions or even trillions of old stars, all orbiting the galactic center in every random direction like a swarm of bees. How do they form? The leading theory is that they are the result of massive collisions. When 2 or more spiral galaxies like our Milky Way and Andromeda crash into each other, their orderly rotating disks are completely destroyed. The stars are thrown into new random orbits and the gas clouds all smash together at once, triggering one final colossal burst of star formation, a starburst. After this burst, all the gas is used up or blown away. The chaotic mess of stars eventually settles down into one giant disorganized retired elliptical galaxy. Irregular galaxies. These are the misfits of the cosmic zoo. As their name suggests, they have no clear defined shape. They have no central bulge, no disk, and no spiral arms. They are chaotic, messy splashes of stars and gas. These are the cities in the middle of reconstruction, or accident sites. An irregular shape is almost always a sign that something dramatic has happened. They are often the result of galactic collisions or near misses called gravitational interactions. When one galaxy passes too close to another, gravity acts like a giant hand pulling and stretching both galaxies out of shape. This gravitational chaos can trigger intense patchy bursts of star formation, making some irregular galaxies shine with the same bright blue light as spiral arms. Our own Milky Way has 2 small irregular satellite galaxies orbiting it called the Large and Small Magellanic Clouds. They are visible to the naked eye from the southern hemisphere, and their messy shape is a result of our own galaxy's gravity tugging on them. Lenticular galaxies. This category is the middle ground between spirals and ellipticals. Their name means lens-shaped. Like a spiral, a lenticular galaxy has a central bulge and a flat rotating disk. But like an elliptical, its disk has no spiral arms and contains very little gas or dust. Think of a lenticular galaxy as a retired spiral. It's a galaxy that used to be a spiral, but it has somehow lost or used up all of its gas. Perhaps it moved into a crowded area, a galaxy cluster where the gas was stripped away by the gravity of its neighbours. It still has the shape and motion of a disk, but the construction sites are all closed. It has stopped making new stars and will now just fade slowly into old age, its disk populated by aging redder stars. The evolution of galaxies. The most important lesson from the cosmic zoo is that galaxies are not static permanent objects. They are dynamic living systems that change dramatically over billions of years. They are not like photos in a museum. They are active players in the universe's grand story. Galaxies eat. Our universe is built on a hierarchical model. This means that small things formed first and then gravity pulled them together to make bigger things. The first galaxies were likely small dwarf galaxies. Over time, these dwarf galaxies collided and merged, building up larger and larger galaxies. This process is still happening. Our own Milky Way is a cannibal. Right now, it is in the process of eating several smaller dwarf galaxies, tearing them apart with its gravity and absorbing their stars into its own structure. Galaxies feed. They don't just eat other galaxies, they also feed on the universe itself. The vast empty spaces between galaxies are not truly empty. They are spanned by a cosmic web of invisible dark matter and thin filaments of hydrogen gas. Galaxies move along this web, pulling in streams of this cold gas, which then trickles down into the disk and provides fresh fuel for making new stars. This feeding process is what allows a spiral galaxy to keep building stars for billions of years. Galaxies collide. This is the most dramatic form of evolution. Space is so vast that when two galaxies collide, the individual stars almost never hit each other. They simply pass by like ghosts. However, the gas clouds are enormous and they do slam into each other, triggering spectacular bursts of star formation. The immense gravity of the two galaxies pulls them into a chaotic dance that can last for hundreds of millions of years. They pull apart, swing back, and eventually merge into one single larger galaxy. This is our own future. The Andromeda Galaxy is not stationary. It is hurtling toward our Milky Way at over 250,000 miles per hour. In about 4.5 billion years, the Milky Way and Andromeda will begin a titanic collision. Over the following billion years, they will tear each other apart and merge. The beautiful spiral disks will be destroyed, and a new giant elliptical galaxy, which astronomers have nicknamed Milkomeda, will be born from the remnants. The different types of galaxies in Hubble's zoo are not just separate categories. They are snapshots of a single epic story, a story of birth from gas growth through feeding and merging and eventual retirement as they use up their fuel and settle into old age. In our last journey, we found our place among our closest neighbours. We discovered our own Milky Way, a vast spiral of stars, and its twin Andromeda, already moving toward us in a slow, gravitational dance. We found our local group, our quiet cosmic family. It feels comfortable, it feels known, but now we must continue our journey. I need you to let go of that anchor. Let's drift upward far above the plane of our galaxy. The Milky Way's bright disk shrinks below us, looking like a glowing pinwheel. Andromeda is a smudge of light nearby. The other 50 or so galaxies of our local group are like tiny scattered jewels. From this height, we begin to feel a pull, a slow, persistent, irresistible tug. Our entire local group, every galaxy in it, is moving. We are not floating aimlessly, we are being drawn towards something immense. We turn our gaze in the direction of that pull toward the constellation Virgo. And there we see it. It's not a single galaxy, it's a city, a glowing, sprawling, ancient metropolis of light. This is the Virgo cluster. If our local group is a quiet suburban street, the Virgo cluster is the bustling, dense downtown core of our cosmic city. It's located about 54 million light-years away, and it is enormous. It doesn't have 50 galaxies, it has over 1,000. Some astronomers estimate it might be as many as 2,000. Giant elliptical galaxies, massive spiral galaxies, and countless dwarf galaxies are all swarming together, bound by a gravitational field so powerful it dominates our entire region of space. At its heart sits a true giant, a monster elliptical galaxy called Messier 87. This galaxy is a beast. It's home to several trillion stars, making our Milky Way look modest in comparison. And at the centre of Messier 87 is the supermassive black hole that humanity famously photographed, a dark shadow 6.5 billion times the mass of our Sun. This entire cluster, this swarm of 1,000 galaxies, is the gravitational anchor of our neighbourhood. Our small local group is just one of many groups on the outskirts, like a small village on the edge of a massive empire. and we are falling toward it. Every second our local group is moving closer to the Virgo cluster, pulled in by its immense gravity at a speed of over 200 miles per second. For a long time we thought this was our ultimate destination. We thought the universe was organised into these great clusters and that the Virgo cluster was ours. We were wrong. Bong! It was so much bigger than that. We must pull our view back again, farther. We see the Virgo cluster, a bright knot of light. We see our own local group, a tiny speck on its edge. But as we zoom out, we see other clusters. The Fornax cluster, the Eridanus cluster, dozens of them. And we notice something incredible. They are all connected. The Virgo cluster, as massive as it is just one part of a single, even grander structure. In 2014, astronomers finally mapped this structure. They didn't just look at where the galaxies are, they looked at where they are going. They traced the gravitational pathways, the rivers of galactic motion, across hundreds of millions of light years. They discovered that our local group, the Virgo cluster, and about 100,000 other galaxies are all part of one colossal system, all flowing toward a common center. They named this structure Laniakea. In the Hawaiian language, Laniakea means immense heaven, and it is. It is our home supercluster. It is a structure so vast it staggers the mind, stretching over 520 million light years from end to end. Think of it like a watershed on Earth. You have tiny streams that flow into creeks, creeks that flow into rivers, and rivers that all flow into the same massive ocean basin. In Laniakea, individual galaxies are the streams. Galaxy groups are the creeks. Great clusters like Virgo are the rivers. And all of them, all 100,000 galaxies, are flowing along gravitational pathways toward one central point in the basin. This central point, the Great Attractor, is the gravitational center of our supercluster. It's a region of space so massive that it pulls everything in Laniakea toward it. We can't see it clearly because it lies on the other side of our own Milky Way, hidden by the dust and stars of our galaxy's disk. But we know it's there. We feel its pull. We are a part of this flow. Our galaxy, our sun, our planet, and you lying here are all part of this grand, silent cosmic river of light drifting through the immense heaven of Laniakea. And now, for the final greatest leap, we pull back one last time. We see Laniakea, our home, as a massive glowing continent of light. But we don't stop. We pull back and back and back until Laniakea itself is just one bright knot among many. From this ultimate vantage point, billions of light years across, we see the universe for what it truly is. We see that the galaxies are not scattered randomly like dust sprinkled on a black table. We see a structure, a pattern, an intricate glowing and impossibly large design. We call it the cosmic web. This is the largest scale structure in the entire universe. It looks like a sponge, or a spider's web. Or perhaps most beautifully, it looks like the neural network of a brain. On this scale, the universe is a network of brilliant shimmering threads that stretch across the darkness, connecting at bright, dense nodes. These threads are the highways of the cosmos, and the nodes are the superclusters, the great cities like Laniakea. These threads are called filaments. The filaments are the most important part of the web. They are colossal tube-like structures of gas and dark matter stretching for hundreds of millions of light years. They are the cosmic highways that the user prompt mentioned. Galaxies are not just in the filaments. They are formed within them, and they flow along them like beads on a string. Gravity pulls matter along these threads, channeling it toward the intersections. The filaments of the transportation network of the universe, delivering gas and galaxies to the cities, the superclusters where they merge and grow. Our own Milky Way is currently travelling along one of these filaments, a thread in the Laniakea supercluster. This web is not a static object, it is a dynamic living system. It's woven from the two most mysterious substances in the cosmos, dark matter and dark energy. The web itself, the invisible scaffolding, is made of dark matter. We can't see it, but its gravity is what shapes everything. The filaments are in truth just the densest regions of this invisible dark matter scaffold. The galaxies, the stars, the gas, all the things we can see are just the dew that has condensed on this invisible web, allowing us to finally see its beautiful, intricate shape. But if the filaments are the everything, there is also the nothing. In between the glowing threads of the web are vast, dark, empty spaces. These are called the voids. If the filaments are the veins of the universe, the voids are the empty spaces in between. These are not just small gaps. They are the true emptiness of space. They are immense, spherical, and almost perfectly desolate. A single void can be hundreds of millions of light years across, yet contain almost no galaxies, no gas, no matter at all. When we look up at the night sky, we feel like space is empty with just a few points of light. But we are wrong. We live in one of the busiest parts of the universe, a bright filament of it. The voids are the true definition of empty. If our galaxy were in the middle of a void, we would look up at the night sky and see nothing. Maybe one or two other lonely galaxies faint and possibly far away. The sky would be almost pure unbroken black. It's a place of profound, terrifying and beautiful loneliness. This is the universe we live in. It is a cosmos of staggering contrast. It is a delicate web of light and a vast ocean of emptiness. It is a universe of filaments teeming with life and creation, and voids filled with a deep, silent and ancient darkness. As you rest tonight, feel yourself connected to this grand design. You are not floating in a random chaotic void. You are part of a structure. You're a tiny, thinking, feeling part of a cosmic filament. You're a mote of dust flowing in the immense heaven of Laniakea. You're a part of the cosmic web. You're in the most literal sense connected to everything. We have journeyed through the cosmic neighborhood, from our solar system to the vast, swirling disk of the Milky Way, and then zoomed out further to the great clusters of galaxies and the empty voids that separate them. We have seen that the universe is not random. It is built upon an immense, intricate structure, a cosmic web of filaments and nodes, a tapestry of light and darkness stretching for billions of light years. This magnificent ordered structure raises the single biggest question of all. Where did it come from? Why is the universe not just a uniform, boring mist of atoms? How did this grand architecture arise? To answer this, we must become cosmic detectives looking for clues in the deepest reaches of space and time. We must step into the field of cosmology, the story of the universe itself. The Great Expansion. Our first major clue came in the 1920s from an astronomer named Edwin Hubble. He was using the most powerful telescopes of his day to study those fuzzy distant patches of light then called nebulae. We now know them as other galaxies just like our own Milky Way. Hubble was measuring how fast these galaxies were moving, and he discovered something staggering. He found that almost every galaxy he observed was moving away from us. But that wasn't all. He found a pattern. The farther away a galaxy was, the faster it was moving away. A galaxy twice as far away was receding twice as fast. A galaxy 4 times as far away was moving 4 times as fast. This precise relationship is now called Hubble's law. What could this mean? Does it mean we are at the center of the universe and everything is running away from us? Not at all. Imagine you have a loaf of raisin bread dough that you're about to put in the oven. The dough is space and the raisins are galaxies. As the bread bakes, the dough expands, carrying all the raisins with it. If you were sitting on one raisin, let's call it the Milky Way raisin, you would look around and see every other raisin moving away from you. A raisin that was nearby would move away slowly. A raisin that was far away on the other side of the loaf would have much more expanding dough between you and it, so it would seem to be moving away much faster. This is exactly what Hubble saw. The space between the galaxies is stretching. It's not that galaxies are flying through space like rockets. It's that space itself is expanding and carrying the galaxies along for the ride. This was a revolutionary idea. The universe was not a static, unchanging stage. It was a dynamic, growing and evolving thing. Rewinding the cosmic clock. This discovery of an expanding universe has a profound and unavoidable implication. If the universe is getting bigger, then in the past it must have been smaller. If we take our movie of the universe and run it in reverse, we see all those raisins in the bread. All those galaxies in space moving closer and closer together. The further back in time we go, the closer they get. Keep rewinding. All the matter in all the hundreds of billions of galaxies we can see would be squeezed into a smaller and smaller volume. As you squeeze matter together, it gets hotter and denser. If you keep rewinding this cosmic clock, you eventually reach a point where all the matter, all the energy, all of space itself is compressed into an infinitesimally small, unimaginably hot and dense. This moment, this origin point for everything, is what we call the Big Bang. It is crucial to understand what the Big Bang is not. It was not an explosion in space like a bomb going off in an empty room. There was no room for it to explode in, there was no outside. The Big Bang was the expansion of space itself. It was the beginning of space, the beginning of time, and the beginning of all the matter and energy that fills our universe. From that single hot, dense point, space began to stretch, and it has been stretching ever since. In the first fractions of a second, the universe was a chaotic, sizzling soup of fundamental particles and energy hotter than the center of any star. As it expanded, it cooled. Within the first few minutes, it had cooled enough for the first building blocks of matter to form protons and neutrons, which then fused together to create the first atomic nuclei. The universe cooked almost all the hydrogen and helium that exist today in those first few minutes. The echo of creation. This story is incredible, but is it true? How can we possibly know what happened 13.8 billion years ago? An idea this big needs big evidence, and we have it. If the universe began in an incredibly hot, bright state, then that fireball of light and heat should still be here. The universe should be filled with the leftover glow, the afterglow of its fiery birth. For the first 30,000 years after the Big Bang, the universe was still too hot for stable atoms to form. It was a plasma, a fog of free-floating protons, neutrons, and electrons. This hot fog was opaque. Light in the form of photons couldn't travel far. It would immediately smash into a free electron, get absorbed, and be re-emitted in a random direction like a pinball in a hyperactive machine. You couldn't see through the early universe any more than you can see through the dense hot plasma fog of the sun's surface. But as the universe continued to expand, it also continued to cool. After about 380,000 years, it reached a cool 3,000 degrees Celsius. At this temperature, the electrons finally slowed down enough to be captured by the protons, forming the first stable atoms of hydrogen and helium. This event, called recombination, changed everything. Suddenly, the fog cleared. The electrons were now safely locked inside atoms, and the photons of light were free to travel. The universe became transparent for the first time. That first flash of light released from every single point in the universe at the same moment began its long journey through space, streaming outwards in all directions unhindered. Where is that light now? It's still here. It's all around us. We are at this very moment bathing in the afterglow of the Big Bang. But there's a catch. For the last 13.8 billion years, the universe has been expanding. And as we learned from Hubble, the light travelling through that expanding space gets stretched. The stretching of light waves makes them redder. This is redshift. This ancient light, which started as bright, visible light like a white-hot fog, has been stretched so profoundly that it's no longer visible light. It's not even infrared. It has been stretched all the way into the microwave part of the spectrum. This is the cosmic microwave background, or CMB. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were trying to use a large radio antenna for experiments. They were frustrated by a persistent faint hiss in their signal. It was everywhere. It didn't matter where they pointed the antenna, it was there day and night. They checked for equipment failure. They even cleaned out bird droppings from the antenna, but the hiss remained. At the same time, physicists at nearby Princeton University were predicting exactly this. They realized that if the Big Bang theory was true, this ancient stretched-out light must exist. When the two groups connected, they realized what the hiss was. Penzias and Wilson had accidentally found the smoking gun, the echo of creation. When we build satellites that can see microwaves, we can take a picture of this light. What we see is an astonishing baby picture of the universe as it looked just 380,000 years after it was born. It is the oldest, most distant thing we can possibly see. The seeds of the web. This baby picture does more than just prove the Big Bang happened. It also holds the answer to our original question: where did the cosmic web come from? When scientists first predicted the cosmic microwave background, they assumed it would be perfectly smooth, the same temperature everywhere. But if the early universe was perfectly smooth, then gravity would have nothing to pull on. The gas would just spread out evenly as the universe expanded. No stars would form, no galaxies, no cosmic web. We wouldn't be here. For the universe to look the way it does today, the early universe must have had some tiny imperfections. There must have been some spots that were just slightly denser than others. When our satellites like the COBE-DUMAP and Planck took high-precision pictures of the CMB, they found them. The hiss is not perfectly uniform. It is covered in tiny faint ripples or blotches. These are minuscule variations in temperature. Some spots are just 1/100,000th of a degree, 0.001 degrees hotter or colder than the average. These tiny ripples are, without exaggeration, the most important discovery in all of cosmology. Those slightly cooler spots in the baby picture are the slightly denser spots. They had a tiny bit more matter, a tiny bit more gravity than the spots around them. They were the seeds of structure. Over the next billion years, gravity went to work. Dark matter, which we cannot see, but which makes up most of the matter in the universe, was pulled toward these slightly denser seeds. As the dark matter gathered, its gravity became even stronger, creating deep gravity wells. These wells then began pulling in the regular matter, the hydrogen and helium gas from all around. The slightly hotter, less dense spots had less gravity and were left behind. They were emptied out, becoming the great voids. The slightly denser regions pulling in more and more material became the filaments, and where the filaments crossed where the pull of gravity was strongest, the gas and dark matter collapsed to form the first stars, the first galaxies, and eventually the massive superclusters we see today. That vast, magnificent cosmic web is not an accident. It is the direct descendant of those impossibly small ripples in the afterglow of the Big Bang. When we look at a map of the CMB, we are looking at the blueprint for the entire universe. Those tiny ancient seeds grew up over 13.8 billion years to become the grand interconnected structure of galaxies that fills our cosmos. We've spent so much time together, now journeying through the visible. We've seen the birth of stars, the silent dance of galaxies, the great shimmering tapestry of the cosmic web that connects everything. It feels vast. It feels like everything. But what if it isn't? What if everything we can see, all the light, all the matter, every galaxy and nebula is just the thinnest layer of foam on top of a deep, dark and impossibly vast ocean? What if the real universe, the forces that truly govern existence, are completely invisible to us? This is the part of our journey where we leave the shores of the known. We're stepping into the darkness, and in that darkness we find two of the greatest mysteries ever to confront the human mind. They are the invisible architects of our cosmos, dark matter and dark energy. Let's start with the mystery of connection. The mystery of why everything isn't flying apart. Imagine, if you will, one of those beautiful spiral galaxies. You can see it in your mind's eye, a spinning pinwheel of 100 billion stars. It's turning slowly and gracefully. Now, physics gives us a very clear rule for things that spin. If you think about our own solar system, the planets closest to the center, like Mercury, move incredibly fast. The planets on the outer edge, like Neptune, move very, very slowly. The pull of gravity gets weaker with distance, so to stay in orbit you have to move slower the farther out you are. It's a simple, elegant rule, and we assumed for decades that galaxies work the same way. The stars on the outer rim of that pinwheel should be moving much more slowly than the stars near the bright dense center. In the 1970s, an astronomer named Vera Rubin decided to check. She was a brilliant and meticulous scientist working in a field dominated by men. She didn't assume, she measured, using powerful telescopes as she looked at the light from the edges of distant galaxies. And the light told her a story that no one was expecting. The stars on the outer edge, they weren't moving slowly. They were moving just as fast as the stars near the center. This was wrong. It was impossible. It was as if you found that Pluto was orbiting the Sun at the same speed as Mercury. At that velocity, with so little visible matter to hold it, that star should just be flung off into the void. The galaxy should tear itself apart. It should have disintegrated billions of years ago. And yet there it was, whole, stable, spinning. Vera Rubin looked at this impossible data, and over again her measurements confirmed it. The galaxy was not flying apart. She and others were forced to a revolutionary conclusion: there must be something else there. Something we can't see. Something that isn't stars or gas or dust. An enormous invisible cloud of something that surrounds the entire galaxy, extending far beyond the visible light. This something has mass, and therefore it has gravity. It's this unseen gravity that is providing the extra grip, the cosmic glue holding that fast-spinning star in its orbit. They gave this invisible substance a name: dark matter. Now, the name is a little misleading. It's not dark as in black or shadowy, it's dark as in transparent. It doesn't interact with light in any way, it doesn't glow, it doesn't reflect, it doesn't absorb. Light, radio waves, X-rays, they all pass right through it as if it weren't there at all. This matter is a ghost. It doesn't interact with you or me, it doesn't make atoms, it doesn't form planets. The only way we know it exists is because we can feel its weight. We can see its gravity bending the light from distant galaxies like a cosmic magnifying glass, and we can see it holding our own universe together. When we talked about the cosmic web, that vast structure of the universe, that's really a map of the dark matter. It is the invisible scaffolding of the cosmos. Imagine a giant, intricate structure built in a dark room. The dark matter is the steel beams, the framework, the architecture. The visible matter, the galaxies, the stars, the stuff we are made of, is just the tiny glittering lights strung along those beams. It was dark matter that in the early universe first collapsed under its own gravity, forming immense halos. These halos became the gravitational wells, the cosmic potholes that pulled in the normal visible hydrogen gas. The dark matter provided the blueprint. The visible matter just followed orders. So what is it? This is perhaps the most humbling part. After all these decades, we still have no idea. We know what it isn't. It's not just clouds of regular matter that are hard to see. It's not dead stars or trillions of black holes. The numbers don't add up. It must be something new. Scientists believe it's a new kind of subatomic particle, a particle that's not part of our standard model of physics. They've given it names like WIMPs, weakly interacting massive particles. They have built enormous detectors deep underground in old gold mines, shielded from all cosmic rays, just waiting for one of these ghost particles to finally just once bump into a single atom of normal matter. And so far after all these years, silence. But it is there. It's all around us. It's flowing through this room, through your body right to now. It is the vast, silent majority of all the stuff in the universe. It is the invisible hand that keeps our own Milky Way from flying to pieces. We are guests in a house built by an architect we have never seen. And as strange as that is, it's only half of the story. Dark matter is the glue. It pulls things together. For a long time, we thought the story of the universe was a simple tug of war. On one side, you have the initial push of the Big Bang flinging everything outward. On the other side, you have the constant pull of gravity from all the matter, and now all this new dark matter trying to pull everything back together. For most of the 20th century, the only question was who wins? Will gravity eventually slow the expansion down to a stop and the universe will just grow cold and dark, or is there enough gravity to not only stop the expansion but reverse it, pulling everything back together in a big crunch? That was the mystery, the slowdown. Then in the late 1990s, two teams of astronomers set out to measure exactly how much the universe was slowing down. To do this, they used a special kind of exploding star, a Type 1a supernova. These supernovae are wonderful because they all explode with almost the exact same brilliant brightness. They are standard candles. If you see one that looks faint, you know it's very, very far away. If you see one that looks bright, you know it's close. So these teams pointed their telescopes at the deepest, darkest parts of space. They found these distant ancient supernovae. They measured their faintness to see how far away they were, and they measured their light to see how fast they were moving away from us. And the results came back. And they were not just wrong, they were shocking. The universe wasn't slowing down. The distant supernovae were even fainter than they were supposed to be. They were farther away than all our models predicted. The only way that could be true is if the expansion of the universe somewhere in the deep past had sped up. It was a discovery that turned all of cosmology on its head. It was like throwing a ball up into the air and watching it not just slow down, but suddenly rocket off into the sky faster and faster. Something was pushing it. There is a force in the universe. A force we had never accounted for. A mysterious repulsive anti-gravity that is built into the very fabric of space itself. This force was given a name just as mysterious as its counterpart dark energy. If we know nothing about dark matter, we know less than nothing about dark energy. It is the single greatest mystery in all of physics. It doesn't seem to come from any particle. It seems to be a property of the vacuum, a property of empty space. It seems that empty space, true nothingness, is not empty at all. It is filled with a latent roiling energy. And here is the strangest part: as space expands, more of this energy appears. Think about it. As the universe gets bigger, the dark matter gets spread out and its gravitational pull gets weaker. But as the universe gets bigger, more space is created. And if this energy is a property of space itself, then more space means more dark energy. More push. For the first few billion years of the universe, dark matter was in charge. Gravity was winning and the expansion was in fact slowing down. But as the universe kept growing, all that new space created more and more dark energy, until about 6 billion years ago it reached a tipping point. The push of dark energy became stronger than the pull of gravity, and at that moment the universe put its foot on the accelerator, and it has been speeding up ever, pushing the galaxies away from each other faster and faster into a future where the night sky will eventually be empty. So let's step back. Let's look at the final complete picture of the cosmos, the complete budget of reality. Everything we can see, you, me, this planet, the sun, every star in our galaxy, every galaxy in the entire observable universe, all the visible matter, adds up to less than 5%. 5. Everything else is hidden. About 27% of the universe is the invisible scaffolding, the cosmic glue dark matter. And the rest, the overwhelming majority, about 68%, is this mysterious accelerating repulsive force, dark energy. This is the universe we live in. We are strangers in our own home. We are tiny particles of light, floating on a vast dark ocean being pushed by a wind we cannot feel. There is a profound humility in this. As you lie here resting, letting go of the day, you can let go of the need to have every answer. You can let go of the idea that we are the center of it all. We are just waking up. We have just in the last few moments of cosmic time opened our eyes and are beginning to see the true shape of the night. It is not a failure to be surrounded by mystery. It is an invitation. It is the universe reminding us that there is always more to explore. It is a cosmic whisper telling us to stay curious. So now just rest. Rest in the knowledge that you are part of a reality so much grander, so much stranger, and so much more magnificent than you can possibly imagine. Rest held together by a force you cannot see expanding into a future you cannot know. If dark energy continues to push everything apart faster and faster, the universe is not heading toward a fiery collapse. Instead, it is sailing toward a future of profound quiet and unimaginable emptiness. This destiny isn't a sudden event, a cosmic crash, or a dramatic explosion. It is a slow, gradual, and inevitable fading. It is known as the Big Freeze, or perhaps more accurately, the heat death of the universe. To understand this future, we must think in terms of timescales that make our minds ache. The entire 13.8 billion year history of our universe from the Big Bang to this very moment is just the first tick of a clock that will keep ticking for trillions upon trillions of years. We are living in the bright, energetic morning of the cosmos. The Big Freeze describes the long cold twilight and the endless night that will follow. The fading sky. The first major change will happen in our sky. Right now, when we look up with powerful telescopes, we see billions of other galaxies. We see the beautiful spiral of Andromeda, our nearest large neighbour, which is actually on a collision course with our own Milky Way. This collision, which will form a new giant galaxy nicknamed Milkomeda, is a local event. It's like two ships in a small fleet drawing together. But dark energy is stretching the ocean of space between all the other fleets. As time goes on, this stretching accelerates. The galaxies that are not already bound to us by gravity will be pushed away faster and faster. First, their light will stretch, shifting to the red end of the spectrum, and then beyond red into invisible infrared light. Then billions of years from now, they will be moving away from us so fast, faster than the speed of light itself, which is possible, because space is stretching, not the galaxy moving through space, that their light will never be able to reach us, at all. One by one, they will vanish from our view. The night sky outside our own local group of galaxies will become completely black and empty. The universe beyond our new giant Milkomeda galaxy will be gone forever, not destroyed but simply unreachable. We will be an island universe isolated and alone in an expanding darkness. The last lights go out. Inside our isolated island galaxy, things will continue for a very long time. This is the age of stars. Our own sun will burn out in about 5 billion years, swelling into a red giant before puffing off its outer layers and settling down as a cold, dense ember called a white dwarf. More massive stars will explode in brilliant supernova, leaving behind superdense neutron stars or black holes. But the universe is filled with tiny, dim red dwarf stars. These are the most common stars, and they are cosmic misers. They sip their hydrogen fuel so slowly that they can live for trillions of years. They will be the last lights in the universe. Long after our sun is a cold cinder, these faint red suns will still be glimmering in the darkness, warming their frozen, lifeless planets. For trillions of years, they will be the only beacons in the black. But nothing lasts forever. The gas and dust needed to form new stars will eventually be used up or spread too thin. The star factories will shut down, and one by one, over a period of time so long it's hard to write, perhaps 100 trillion years, even the last red dwarf will burn through its last drop of fuel. It too will cool down, becoming a black dwarf, a cold dead crystal floating in the dark. The universe will then enter the age of star remnants. It will be a graveyard. A vast dark sabois populated only by the cold corpses of stars' black dwarfs, neutron stars and black holes. Frozen planets will orbit these dead stars or wander alone as orphans having been flung out of their solar systems. The final eras. The universe will be almost completely dark, but it won't be completely dead. Two things will still be happening on timescales that make the age of stars seem like a blink. The first is the slow dance of gravity. Over trillions and trillions of years, the leftover dead stars and planets will slowly interact. Some may be flung out of the galaxy into the void. Others will slowly spiral inward, eventually being swallowed by the giant black holes that sit at the center of every galaxy. The second process is even slower, the end of matter itself. This leads to the black hole era. Over an almost truly infinite amount of time, even black holes will not last. A physicist named Stephen Hawking discovered that black holes are not completely black. They leak a tiny amount of energy called Hawking radiation. This process is impossibly slow for a large black hole, but it is constant. Over a period of 10 to the power of 100 years, a number so large it has no name, we can comprehend even the biggest black holes will slowly evaporate, shrinking and finally disappearing in a tiny puff of light. And what about the dead stars, the black dwarfs and neutron stars? There is an idea in physics that even the protons, the building blocks of atoms, are not perfectly stable. If this is true, then over these same unimaginable timescales, all remaining matter will simply fall apart. Every dead star, every frozen planet, every speck of dust will dissolve into a thin soup of basic particles and radiation. The Big Freeze. This is the final step. The Dark Era. After all the stars have died, all the black holes have evaporated, and all matter has perhaps decayed, the universe will be almost empty. It will be a void of unimaginable size, still expanding, still getting colder. It will be filled with only a few scattered particles, photons, neutrinos, electrons drifting farther and farther apart from each other. The temperature of the entire universe will drop to a tiny fraction of a degree above absolute zero, the coldest temperature possible. This is the heat death. It doesn't mean the universe burns up, it means the death of heat difference. Life and all interesting activity rely on differences like the heat from the sun flowing to the cold of space. When everything is the same temperature, no work can be done. No energy can flow. It is a state of perfect unchanging equilibrium. The universe will be cold, dark and empty, a state of final permanent stillness. This isn't a future to fear, it's perhaps a concept that gives us perspectives. It tells us that time is vaster than we can ever know, and that change is the only true constant. The entire story of our universe, our Earth, our struggles, our triumphs, our civilizations is a brilliant, precious and fleeting flash of light and warmth. We are living in the prime of the cosmos, a brief energetic moment when stars are shining and life is possible. The long cold night that follows is just the natural slow and quiet end to a magnificent story. We have travelled an immense distance together. We have crossed billions of years from the very first spark of light to the birth of galaxies. We have witnessed the slow, patient formation of stars and planets. We have explored the strange laws that bend space and stretch time, and we have searched the darkness for echoes of other lives, other minds. But after that journey across all of space and all of time, we must return. We must come back to the only place we have ever truly known. We are here, right now. Feel the air move in and out of your lungs. Feel the simple, solid ground beneath you. After all our exploration of the cosmos, the journey ends exactly where it began in this moment. You are here, a fleeting but finite consciousness floating in the middle of an ocean of mystery. And who are you? You are not just an observer of this universe, you are the universe. This is not a metaphor, it is a literal truth. Look at your hand. Every single atom in your hand, every atom that makes up your body was created in a place of unbelievable violence and power. The carbon that forms the basis of your cells, the oxygen you just breathed in, the iron in your blood that carries that oxygen, none of it was made here. It was forged long ago in the heart of a star. Our planet and everything on it is built from the ashes of stars that lived and died billions of years before our sun was ever born. These giant stars were the universe's first factories. For millions of years, they fused simple elements into heavier ones. When they finally exhausted their fuel, they exploded in magnificent supernovae, scattering those new precious elements across the galaxy. That cosmic debris that stardust drifted through space for eons. Eventually it gathered, drawn together by gravity to form a new solar system. It formed our sun, it formed our planet, and it formed you. As the great astronomer Carl Sagan famously said, we are made of star stuff. We are the children of the stars. When you look up at the night sky, you're not looking at something separate from you. You're looking at your own ancestry, and this leads to perhaps the most profound idea of all. For 13.8 billion years, the universe expanded. Galaxies spun, stars burned, and planets formed all in silence. It was an immense, complex, and beautiful machine, but it was not aware of its own beauty. The atoms and energy existed, but they did not know they existed. Then, on this small, wet rock in this quiet corner of one galaxy among billions, something changed. That star stuff, that collection of carbon, oxygen, and iron organized itself. It became life. And after billions of years of slow evolution that life woke up, it became us. Through our eyes, the universe is finally seeing itself. Through our minds, the universe is beginning to understand itself. When you feel a sense of wonder, it is the universe feeling wonder at its own existence. When you study the laws of physics, it is the universe attempting to read its own instruction manual. We are the means by which the cosmos has become self-aware. We are not just in the universe, we are the universe, we are the part that woke up. But this realization brings with it a powerful and unsettling question. We are here. We are alive and thinking and looking out. Where is everyone else? This is the great silence, the Fermi paradox. Our galaxy alone contains hundreds of billions of stars. We now know that most of those stars have planets. There should be billions, perhaps trillions of planets just in our own Milky Way that are habitable, existing in that gentle zone where liquid water can flow. If life can start here, why not there? If it started billions of years before us on a planet older than Earth, that civilization could be millions of years more advanced than we are. They should have spread across the galaxy. We should see their signals, their structures, their space crawl. But we see nothing. We hear only silence. The universe seems empty. There are many possible answers, and we don't know which one is true. Perhaps life is incredibly rare and we are the first to wake up. Perhaps the distance between stars is just too vast to cross. Perhaps civilizations, once they reach a certain point of technology, inevitably destroy themselves. Or perhaps they are out there watching us hiding in a way our simple senses cannot detect. We don't know, but the silence leaves us with a feeling of deep, profound loneliness. It makes us realize how incredibly precious this one small pale blue dot really is, and so we are left here on our speck of dust floating in a vast dark ocean with this new understanding. We are made of stardust. We are the universe's way of knowing itself, and we are quite possibly alone. What does this mean for us? What is the purpose of it all? If we have learned anything from Leah's journey, it is that the universe does not hand us a purpose. The meaning of our existence is not some great secret hidden in a distant galaxy waiting to be found. The meaning is right here. It is the meaning we create. The universe is vast and we are small. It is ancient and our lives are just a blink. But in this one brief moment, we get to be a part of it. We get to be the conscious part. We get to feel love and ask questions and create art and look up at the stars and wonder. Our significance does not come from finding the answers. It comes from having the ability to ask the questions. We are the universe's dream. We are the stardust that woke up, and our purpose is simply to be awake, to be aware, to witness the profound, terrifying and beautiful reality that we are a part of. Do not be afraid of the vastness. Do not be diminished by the silence. Find your peace in the knowledge that you are a part of this grand cosmic story. You are not separate from it. You are a unique and sheer, precious expression of it. And for a little while, you get to be here now and simply be.